All right, we're going to work through a couple of the problems that people have asked questions about from section 1.2. The first is this problem where our sequence is defined with a recursive description, but described in English, where we say we're going to start with 2, and each term is the previous term squared. So 2 squared is 4, 4 squared is 16, 16 squared is 256, excuse me, and so on. So the key to this is really, it's not a particularly interesting sequence, but the key is to realize that these are all powers of 2, which makes sense since we're starting off with 2. But the lesson here is that if we think about the form of the answer, often that will allow us to think differently about the way we see it. So we shouldn't be so fascinated with those final numerical values that we lose track of where those numbers come from. So 2, 4, 16, 256 is really 2 to the first, 2 squared, 2 to the fourth, and 2 to the eighth. And so what's happening there is when you square a power, for example, if I take 2 to the fourth and square it, that's going to give me 2 to the 4 times 8. These powers get multiplied together when we raise a power to a power. And so that's why the powers themselves are doubling each time. Every time we square 2 to a power, we get 2 to the power that's twice as much. So because of the squaring, the powers themselves, the things in red, are actually doubling. And so the pattern here, a formula for these guys would just be 2 to the n minus 1. The formula 2 to the n minus 1 gives us 1, then 2, then 4, then 8, and so on. But those aren't the values of my sequence. Those are the values of the powers. So the values in the sequence are 2. Oops, I shouldn't write there. All the values in the original sequence have a 2 as their base, but the power is going to be the thing that we can see the pattern in. So 2 to the 2 to the n minus 1 is actually the formula for the sequence, and it looks fairly awful. But again, the idea is that by not multiplying out these values, in other words, by not trying to get these numerical values necessarily, but leaving them in this form, we can see a much stronger pattern among the exponents than we saw among the numerical value. So there's something to be said for not simplifying answers, for leaving answers sort of unevaluated if you can, and you might see patterns where you're not seeing them in the final evaluated form. The other question that's similar to some of the worksheet problems are these problems where we're starting with a closed formula and we're trying to see if we can find a recursive relationship. I had said in class that the other way around is hard, but this is always fairly straightforward. It does involve algebra, though. So here's what the algebra would look like. If we have this formula, then that means I have a way of calculating a sub anything. If I want a sub 3, I would just change the n into a 3 in both places. If I want a sub 10, I would change the n into a 10 in both places. So I don't have to use numbers to put in there. I can put anything I want in there. A sub k would be 2 to the k minus 1. A sub L would be 2 to the L minus 1. It really doesn't matter what you put in. This statement will always be true. And so what we can do, and I would recommend using a variable other than n, just because it's a little bit easier to think about, is first, and this is the way the worksheets are written, first use n equals m. If you do that, it'll say am is 2 to the m minus 1. Second, use m minus 1 for n. If I do that, that statement that's in the box up there will say that. Again, as long as I can make n anything at all, and that'll be a true statement. So if I want to check this guy in blue, this statement, this is looking at a relationship between a sub something and a sub whatever's previous. So if I want to see if these two things are really equal, this is really an algebra issue. And again, I'm going to do this not with n's here, but with m's, just because it's easier for me to think about changing the subscripts. So on the left side, a sub m is exactly this. So there's an algebraic expression that is equal to a sub m. On the right side, I'm building twice a sub m minus 1 plus 1. So that is twice this thing plus 1. Twice a sub m minus 1 plus 1 is twice this guy here, plus 1. So again, that becomes an algebra issue. So let's ask ourselves, what is algebraically, what do I get when I do that? So again, this is, this part right here is am minus 1. So, so what I have written down here, this is twice a sub m minus 1 plus 1. And I can simplify that algebraically. 2 times 2 to the m minus 1 minus 2 plus 1. All I've done there is I've multiplied this 2 through the parentheses. Now I'm going to use an exponent rule. Since 2 is the same as 2 to the first power, 2 to the first times 2 to the m minus 1 is just 2 to the m. And then I have minus 2 plus 1, which is minus 1. So what I can see from that calculation is that this whole thing, which is 2 times a sub m minus 1 plus 1, has to be equal algebraically to 2 to the m minus 1. And it turns out, in this case, that that's exactly what a sub m was in the first place. Remember, a sub m was right there in that box. So algebraically, a sub m is equal to 2 to the m minus 1, and we can show that algebraically 2 times a sub m minus 1 plus 1 simplifies to 2 to the m minus 1. So those are actually equal. So in this case, the answer would be yes. A sub m here is equal to 2 times a sub m minus 1 plus 1, which was the question. So notice the way we're doing that, we're taking the more complicated side of this, this thing that we're checking up here. This is the more complicated side. And we're starting with that, given that we know the algebra for this. And then we're going to just simplify this and see if it's equal to what we would get by putting m in. So it's a little bit of algebra to keep track of. Once you've done one or two of them, it's easy to see what at least your goal is. And on problem 6, some of those recurrence relations that are shown are true and some of them are not. And you should be able to at least do the algebra simplification for all of them and then see whether or not it's exactly the same algebra statement.